We rarely question solidity. It feels absolute, dependable, almost unquestionable. When you rest your hand on a surface, there is no hesitation in your mind. You expect resistance, structure, certainty. But this confidence does not come from what matter truly is. It comes from how our senses interpret it. The moment we examine matter at its most fundamental level, that certainty begins to dissolve. At the scale of atoms, what appears solid is mostly empty space. Let's replace the usual comparisons with something more precise. If you scale an atom so that its nucleus is about 1 centimeter across, the outer boundary of its electrons would lie roughly 100 meters away. That is the length of a football field. Almost everything in between contains no matter in the way we normally imagine it, only fields and probabilities describing where particles might be. This is a useful teaching insight. When you press your hand against a table, no atoms are actually touching. What you feel as resistance is the result of electromagnetic forces. The electrons in your hand repel the electrons in the table. This repulsion creates the sensation of solidity, not direct contact between particles. In other words, the physical world we trust is held together not by continuous substance, but by forces acting across empty space. Now consider a simple question. What would happen if that empty space were removed? Not reduced, but completely eliminated. Imagine compressing matter so intensely that the distances between particles vanish, and the structure of atoms can no longer survive. This is not a hypothetical thought experiment. Nature performs this compression under very specific conditions. When gravity becomes strong enough, it overwhelms the forces that normally keep atoms intact. Under such pressure, electrons are forced inward. Atomic boundaries collapse. The familiar structure of matter, nuclei surrounded by orbiting electrons, begins to break down. A more accurate way to think about this is through energy scales. The structure of an atom is maintained because electromagnetic forces dominate at ordinary densities. But gravity, when amplified to extreme levels, begins to compete directly with these forces. Once gravitational pressure exceeds the energy holding electrons in place, those electrons can no longer remain in their usual states. The system is forced into a new configuration, one that minimizes energy under entirely different constraints. Somewhere in the universe, this process has already occurred, not gradually, but violently and completely. The result is one of the most extreme objects known in physics, a neutron star. But to understand how matter is pushed to this breaking point, we must first examine the long, delicate balance that keeps stars alive in the first place. That balance we ended with is not unique to extreme stars. It is the defining condition of every star that has ever existed. A star survives only as long as two opposing processes remain in equilibrium. Gravity pulls everything inward, compressing the star's mass toward its center. At the same time, nuclear fusion generates energy that pushes outward, resisting that collapse. This is not a gentle process. It is continuous and exacting. In a star like our Sun, hydrogen nuclei fuse into helium at temperatures exceeding 15 million degrees Celsius. Each fusion reaction releases energy in the form of radiation and particle motion. That energy builds pressure, and that pressure is what prevents the star from collapsing under its own weight. A useful way to understand this is through balance rather than force alone. Imagine a system where any small change corrects itself. If gravity compresses the core slightly, temperature rises. Higher temperature increases the rate of fusion. That produces more energy, which pushes outward and restores equilibrium. Stars regulate themselves in this way for most of their lives, but this stability depends on one condition: a continuous supply of fuel. Hydrogen is abundant, but not infinite. In the Sun, this process can continue for about 10 billion years. More massive stars consume their fuel much faster. Their cores reach higher temperatures, which accelerates fusion at a dramatically increased rate. As hydrogen becomes scarce, the star adapts. It begins fusing helium into heavier elements such as carbon and oxygen. In more massive stars, this progression continues further: neon, silicon, and eventually iron. Each stage requires higher temperatures and occurs over shorter timescales. What took millions of years early on may take only days in the final stages. Here is an important teaching insight. Fusion releases energy only when forming elements lighter than iron. Up to that point, the process supports the star. Beyond it, the rules change. When the core becomes dominated by iron, fusion no longer provides outward pressure. Instead of releasing energy, it begins to consume it. The balance that sustained the star for millions or billions of years starts to fail, and when that happens, the system does not slowly adjust. It loses stability entirely. Gravity, which has been held back for so long, begins to take control. What follows is not a gradual transition, but a rapid and irreversible collapse. When that balance fails, the change is not gradual. It is immediate and unforgiving. The presence of iron in the core removes the very mechanism that sustained the star. Fusion can no longer respond to compression. There is no corrective process left. At this point, the core exists in a state of unstable equilibrium. The moment gravity gains even a slight advantage, collapse begins, and once it starts, it accelerates rapidly. The timescale is important here. We are not dealing with thousands or even seconds in any familiar sense. The entire core collapse happens in less than a second. In that brief interval, a region comparable in size to Earth contracts to something closer to a large city, roughly 10 to 20 kilometers across. This is not compression in the ordinary sense. It is a structural failure of matter under extreme gravitational pressure. The inward acceleration becomes so intense that particles are forced into configurations they would never occupy under normal conditions. A useful way to think about this is through free fall. If you drop an object on Earth, gravity accelerates it steadily. Now imagine that acceleration increased by orders of magnitude, and that every part of the object experienced it simultaneously, directed toward a common center. That is closer to what happens inside a collapsing stellar core. As the core contracts, densities rise sharply. Protons and electrons are pushed closer together, and the energy of the system increases dramatically. This energy does not remain contained. It is released in several forms, but most significantly as neutrinos, particles that interact so weakly with matter that they escape almost immediately. In fact, the majority of the energy generated during collapse leaves the star in the form of neutrinos. This is a useful teaching point. Although the visible explosion is immense, it represents only a small fraction of the total energy involved. Meanwhile, the outer layers of the star are still falling inward. When the collapsing core reaches extremely high densities, it becomes resistant to further compression. This sudden resistance creates a rebound effect. The infalling material crashes into this dense core and is driven outward. The result is a shock wave that propagates through the star. When it reaches the surface, it tears the star apart in a supernova explosion. For a short time, the brightness of this single event can exceed that of an entire galaxy. But this explosion, as dramatic as it is, does not erase the core. What remains is no longer a star in the usual sense. It is a compact object, formed under conditions where the familiar structure of matter has already begun to break down, and this remnant will carry forward the consequences of that collapse, leading us directly to the extreme densities we must now examine. What remains after that collapse is no longer governed by the rules we associate with ordinary matter. The core that survived is compact, stable, and extraordinarily dense. To understand it, we must set aside everyday intuition and work with scale more carefully. A typical neutron star contains a mass comparable to 1.5 to 2 times that of the Sun. Yet all of that mass is confined within a sphere roughly 10 to 12 kilometers in radius. This is not a gradual compression. It is a concentration of mass so extreme that familiar comparisons begin to fail. Let us approach it quantitatively. The average density of such an object exceeds 10 to the power of 17 kilograms per cubic meter. For context, the density of an atomic nucleus is on the order of 10 to the 17th power kilograms per cubic meter as well. This means the interior of a neutron star is comparable to, and in some regions exceeds, the density found inside individual nuclei. A simple numerical illustration helps clarify this. If you could isolate a volume of material the size of a teaspoon from this object, its mass would be on the order of 1 billion tons. This is not an exaggeration. It follows directly from the density values we just considered. This concentration of mass produces equally extreme gravitational effects. The surface gravity of a neutron star is approximately 10 to the 11th power times stronger than that of Earth. A person standing there, if that were even possible, would experience forces that exceed any known material strength. Even light is significantly affected. The escape velocity approaches a substantial fraction of the speed of light, meaning radiation struggles to leave the surface. There is another factor that becomes important here: magnetic fields. Neutron stars can possess magnetic fields on the order of 10 to the 8th power to 10 to the 11th power Tesla. For comparison, the strongest steady magnetic fields produced in laboratories reach only tens of Tesla. This difference is not incremental, it is many orders of magnitude. A useful teaching insight is this: that such field strengths, or atoms, if they could exist, would be stretched and distorted along magnetic field lines. The electromagnetic structure we discussed earlier would no longer behave in familiar ways. What we are observing is not simply compressed matter. It is matter in a regime where gravity, quantum mechanics, and nuclear forces all operate at comparable scales. None of them can be ignored. This is why it is more accurate to say that matter here has been transformed, rather than merely compressed. Its internal structure, its interactions, and even its identity begin to change under these conditions. And to understand how that transformation unfolds, we must now examine the internal structure of this object, layer by layer. To examine that internal structure, we must now focus on what happens to matter under these conditions, not just in terms of compression, but in terms of identity. The key point is simple but profound. The atomic structure we rely on cannot survive here. At sufficiently high densities, electrons are no longer able to occupy stable positions around nuclei. The pressure forces them inward, reducing the space available for their quantum states. Eventually, a critical threshold is reached where it becomes energetically favorable for electrons to combine with protons. This process is known as inverse beta decay. A proton captures an electron and transforms into a neutron, releasing a neutrino in the process. What matters here is not just the reaction itself, but its consequence. The number of free electrons decreases, and the matter becomes increasingly dominated by neutrons. A useful teaching insight is this: electrons, through their motion and quantum properties, provide a significant portion of the pressure-resisting compression in dense matter. When they are removed, that resistance weakens. Gravity gains further advantage, and the system is driven into an even denser state. This creates a feedback process. Higher pressure leads to more electron capture. More electron capture reduces pressure support. The structure continues to shift toward a neutron-rich configuration. At the same time, vast numbers of neutrinos are produced. These particles interact so weakly that they escape almost immediately, carrying energy away from the system. This energy loss further supports the collapse, allowing matter to settle into a more compact state. What is important to understand is that this is not a surface effect. It occurs throughout regions where density and pressure exceed critical thresholds. The transformation is systematic, governed by energy minimization rather than any single violent event. As this process continues, the distinction between individual atoms disappears. Nuclei lose their identity as isolated structures surrounded by electrons. Instead, matter becomes a dense assembly of particles where neutrons dominate and electrons are increasingly scarce. We are now dealing with matter that is no longer atomic in any conventional sense. Its behavior is governed by nuclear interactions and quantum statistics at extreme densities, and yet this transformation does not occur uniformly from the surface to the center. The conditions vary with depth, and so does the structure of matter. To understand what forms next, we must begin to examine these layers more carefully, starting from the outer regions and moving inward. To follow this transformation further, we must now move inward step by step, because the internal structure of a neutron star is not uniform. Conditions change with depth, and matter responds accordingly. At the very surface, the environment is extreme by terrestrial standards, yet still recognizable in form. Nuclei exist, and electrons surround them, though in far greater densities than anything found on Earth. The arrangement resembles a highly compressed lattice, where nuclei are packed closely together and electrons move freely through the structure. As we descend, pressure increases steadily. This has a direct effect on nuclear stability. Nuclei begin to incorporate more neutrons, shifting toward configurations that would be unstable under normal conditions. These neutron-rich isotopes exist here because the surrounding pressure alters the balance of forces inside the nucleus. A useful teaching insight is this: nuclear stability is not fixed. It depends on the environment. Under extreme pressure, configurations that would normally decay can persist because the system as a whole minimizes its energy differently. Alongside this change, electrons no longer behave as localized particles. They form what is known as a degenerate quantum gas. In simple terms, their behavior is governed less by temperature and more by the constraints of quantum mechanics. They occupy all available low-energy states, creating a pressure that resists further compression. But this resistance has limits. At a certain depth, a critical threshold is reached. This is known as the neutron drip point. The name is descriptive and precise. Nuclei become so saturated with neutrons that they can no longer retain them. Excess neutrons begin to escape, not as isolated events, but as a continuous process. This marks a fundamental transition. For the first time, we encounter free neutrons existing alongside nuclei and electrons. The system now consists of three components interacting simultaneously. To visualize this, imagine a dense arrangement where nuclei act as structured regions, electrons form a continuous background, and neutrons begin to move independently between them. This is not a mixture we observe under any laboratory conditions. The presence of free neutrons changes the mechanical properties of the material. It introduces new modes of interaction and alters how pressure is distributed throughout the system. And as we continue to move deeper, the pressure does not stabilize. It increases further, pushing nuclei toward even more extreme configurations. Eventually, even these neutron-rich nuclei can no longer maintain their structure. The forces holding them together are overcome by the surrounding conditions. What follows is not a gradual adjustment, but the beginning of another transformation, where structured nuclear matter gives way to entirely new forms. As pressure continues to rise beyond this point, the system can no longer sustain nuclei as distinct spherical structures. The competition between forces becomes more intense, and the matter begins to reorganize itself in ways that are both unexpected and highly structured. To understand this, we need to consider two influences acting simultaneously. The strong nuclear force pulls protons and neutrons together at very short distances. At the same time, electromagnetic repulsion pushes positively charged protons apart. Under ordinary conditions, this balance results in compact, roughly spherical nuclei. But here, the environment alters that balance. The surrounding pressure compresses matter so tightly that maintaining isolated spheres is no longer the lowest energy configuration. Instead, nuclei begin to merge and reshape, forming extended structures. A useful teaching insight is this: systems under extreme constraints tend to adopt configurations that minimize total energy, even if those configurations appear unusual to us. In this case, geometry itself becomes a response to pressure. Initially, spherical nuclei elongate into rod-like formations. As density increases further, these rods connect, forming sheet-like layers. The transitions are gradual, but the resulting structures are strikingly different from anything found in conventional matter. Physicists have given these phases informal names based on their shapes, terms like spaghetti and lasagna. While the names are simple, the physics behind them is not. These configurations arise from a precise balance between competing forces operating at nuclear scales. What is particularly significant is the strength of these structures. Calculations suggest that this so-called nuclear pasta may be among the strongest materials in the universe. Its resistance to deformation comes from the continuous network of nuclear matter extending across large regions. This has observable consequences. For example, the rigidity of these layers can influence how a neutron star responds to stress, potentially affecting phenomena such as starquakes and rotational irregularities. But even these complex structures are not permanent. As we move deeper, pressure continues to increase, and the distinction between individual formations begins to blur. The organized geometry starts to dissolve. At this stage, matter is approaching a new limit. The idea of discrete structures, whether spherical, rod-like or layered, becomes less meaningful. What lies beyond is a state where matter behaves as a continuous medium, dominated by nuclear interactions rather than identifiable shapes. To understand that state, we must now move further inward, where the behavior of matter becomes increasingly governed by quantum effects on a macroscopic scale. As those structures dissolve, the distinction between organized shapes and continuous matter disappears. What we encounter now is not a lattice, not a layered geometry, but a medium dominated by a single component: neutrons. At these depths, pressure and density have reached levels where neutrons are no longer confined to specific regions. They form a dense, interacting system that extends throughout the outer core. But the most important change here is not composition alone. It is the state in which this matter exists. Under these conditions, neutrons enter a phase known as a superfluid. This is a quantum state in which viscosity effectively vanishes. In practical terms, this means the fluid can flow without losing energy to internal friction. Once in motion, it does not slow down in the way ordinary fluids do. A useful teaching insight is this: superfluidity is not just about smooth flow, it reflects a collective quantum behavior. Instead of acting as individual particles, neutrons pair up in a coordinated way, forming a system that behaves as a single quantum entity over macroscopic distances. This pairing is similar in principle to what occurs in superconductors, and in fact, something comparable happens here as well. The small fraction of protons present in this region forms a superconducting state. Electrical resistance drops to zero, allowing currents to persist without energy loss. Together, these two properties, superfluid neutrons and superconducting protons, create a system unlike anything encountered in everyday physics. Motion and electrical activity occur with perfect efficiency, governed by quantum rules rather than classical ones. We do not observe this state directly, but its effects are measurable. One of the most striking examples comes from pulsars, which are rapidly rotating neutron stars. Occasionally, their rotation rate changes suddenly in events known as glitches. These glitches are understood as interactions between the superfluid interior and the solid outer layers. The superfluid can store angular momentum differently, and when it transfers that momentum, the rotation of the entire star adjusts abruptly. This is a valuable reminder that even at astronomical scales, quantum mechanics can dominate behavior. What we typically associate with microscopic systems becomes relevant across an object tens of kilometers wide, but even this remarkable state does not represent the final layer. As we move deeper still, density continues to increase, and the assumptions we have relied on begin to weaken once again. The question now is not just how matter behaves, but whether the particles themselves remain unchanged under such extreme conditions. As we move deeper still, the challenge is no longer only to describe what matter becomes, but to understand how we can know anything about it at all. At these depths, direct observation is impossible. What we rely on instead are theoretical models, constrained by what little evidence the universe allows us to measure. The central concept here is known as the equation of state. In simple terms, it is a relationship between pressure and density. For ordinary materials, this relationship can be measured directly. We can compress a sample, record how it responds, and construct precise models. But for neutron star matter, this approach fails entirely. A useful teaching insight is this: every prediction we make about a neutron star, its size, its internal layers, even the maximum mass it can sustain, depends on this single relationship. If the equation of state changes, all of those predictions change with it. The difficulty arises because the required conditions cannot be reproduced in laboratories. Even the most advanced facilities can only approach a fraction of the densities found in these objects. As a result, physicists must extend known theories into regimes where they have not been experimentally verified. This process is not guesswork, but it is constrained. Theories from nuclear physics, quantum mechanics, and relativity are combined and tested against astronomical observations. For example, measurements of neutron star masses and radii provide limits. If a model predicts values outside those limits, it is discarded. Another source of information comes from gravitational waves. When two neutron stars collide, the signal they produce carries subtle signatures of their internal structure. By analysing these signals, physicists can refine their understanding of how matter behaves at extreme densities. Yet, even with these tools, uncertainty remains. Different models can satisfy the same observational constraints while predicting different internal compositions. This means that multiple descriptions of neutron star interiors may be consistent with current data. This uncertainty is not a weakness. It is a reflection of the limits of current knowledge. In fact, neutron stars serve as natural laboratories, allowing us to test physical laws under conditions that cannot be recreated on Earth. A simple comparison may help. In most sciences, experiments are designed and controlled. Here, the experiment already exists, and we must interpret it from a distance using only indirect signals. Because of this, neutron stars occupy a unique position in physics. They are not just objects to be described. They are systems that challenge and extend the theories we depend on. And as we approach the very center, even these carefully constructed models begin to lose certainty. The question now becomes more fundamental, not just how matter behaves, but whether our current understanding of matter remains valid at all.